This is lecture 1 for chapter 7, and this lecture will cover sections 7.1 through 7.3. This is our introduction to probability. Let's start off with a little clip from Mythbusters talking about the Monty Hall paradox, and this problem is also described in the first part of chapter 7 in the textbook.
Coming up, Adam and Jamie butt heads. Adam's gonna kick my butt. In order to crunch the Monty Hall numbers in your face. What do you get when you cross a complex probability puzzle with a game show? The answer is the viewer-requested myth known as the Monty Hall paradox. And so far, Adam and Jamie have answered part 1 of the problem. What's it going to be? Are you going to switch or are you going to stick? As far as the psychology of sticking or switching goes,
I'm going to stick with 2.
contestants are unwilling to change their choice. I'm going to stick. So where do we stand?
Well, amazingly, our volunteers chose to stick 100% of the time.
The second part states that we should see a clear statistical advantage to switching. Did we see anything like that in the numbers?
Well, given that nobody decided to switch, we don't really know.
Well, clearly, we should run this again. And I think with an equal number of switching iterations to sticking iterations so that we can really compare the numbers. As Jamie said, with all of the contestants sticking, they don't yet have any data on whether switching is advantageous. So test 2 will focus on the statistical paradox. Is switching, in what appears to be a 50-50 situation, really your best bet? To find out, Adam and Jamie will collect a large and definitive sample of 100 data points with an elegant, mechanical mini game show setup. So what I need to do right now is build a physical Monty Hall paradox testing simulator. And it's a machine. I need to think of it like a machine because there's a lot of moving parts. I'm thinking it's going to have 2 sets of 3 doors, one for me, one for Jamie. It's going to have a roll of 50 tests randomly selected, preloaded so that we can cycle through it really fast. It's not going to be a simple build, but I think in the end it's going to be really cool. All right, let's bring it on in.
This rig serves a couple of functions. First, it increases our sample size, which in turn increases our accuracy. Secondly, it removes the variable of choice from the equation and puts both switching and sticking on an even playing field. We'll show you how you would fare over time with either choice. So this all looks lovely, but how's it work?
You and I are going to run through each of the tests, and each time we win, we take a red piece of paper and we thumbtack it up onto the board behind us.
Okay.
At the end, we should be able to see visually if there's a difference between me always switching and you never switching, and we should be able to count and compare the numbers.
How do I think I'll do? Well, if the myth is true, Adam's going to kick my butt.
To find out, it's pick a door, take 2. Test number 1, choose your door.
I choose 1.
I choose door number 2, open an empty door.
I'm sticking. I lose.
I am switching. I win! Whee! Unlike the previous test,
I choose 1.
I choose 3. Adam and Jamie are focusing only on the win-lose result.
I'm sticking. I lose.
I am switching. I win! Woohoo! The rules are exactly the same. Test number 3. Except the stick or switch variable is removed.
I'm sticking.
Jamie always sticks,
I lose.
and Adam always switches. I am switching. I win! This is crazy. I can't keep winning like this. In addition, the large sample means that over time,
I'm sticking. I lose.
the results will reflect the true probability of the choice to stick or switch.
I'm sticking. I win.
Hey! But it's not long before the results on the board paint a definitive picture. I choose 2.
The Monty Hall paradox is interesting because, on the face of it, it seems simple.
I am switching. I win!
During the final stage of it, you've got 2 choices. You know one of them's a winner and one of them's not, so common sense would tell you that you've got a 50-50 chance of winning, and yet you don't. That's where the paradox comes in.
I am switching. I win 7 in a row in your face. You could talk about the mathematics and the statistics and the theory and the proofs of this story until you're blue in the face. But the only way to make the numbers truly clear is just to do it. The results are crystal clear. Switching is far, far better than sticking with your original choice.
What's going on here is really interesting. If the prize is equally likely to be behind each of the doors, then if a player picks door 1, there's a 1 in 3 chance the prize is behind it. That means that there's a 2 in 3 chance that the prize is behind doors 2 and 3. Now take away door 3, and there's still a 2 in 3 chance that it's behind door 2. So switching effectively doubles your chances of winning. So what advice can we offer our viewers about the Monty Hall paradox?
Well, clearly if you're ever playing this game, you will have an overwhelming urge to stick with your original choice. But given the fact that the host knows where the prize is and shows you an empty door, it is always an advantage for you to switch.
Then it would be confirmed.
Totally confirmed.
So Jamie and Adam did a really nice simulation of the Monty Hall problem. And again, this problem is described in your textbook. And, you know, this is an example of what we call a simulation. And there are many different ways to do simulations, and this is one way. You know, I watch this show with my kids all the time. And when I saw this particular episode, I thought, boy, I got to capture this for my students and show it to them. Because again, it's a really great example of a simulation. Now we're going to talk about another type of a simulation as well. And we're going to use the calculator this time. And in this case, I want to talk about what I call the fair coin model. And the idea here is, you know, we're going to simulate flipping a fair coin. The first thing we're going to have to think about is what's our definition of a fair coin? And one way to think about the definition is to think about a fair coin as producing the same number of heads as tails in the long run. And if we think about this in terms of probabilities, then what we could say is that the probability of heads equals the probability of tails which is equal to 1/2. Now, if I'm going to simulate this on the calculator, what I need is a feature or a application on the calculator that can give me a random sequence of heads and tails from what we call a uniform distribution. So what I'm going to use is something called a random number generator, and in particular the one I'm going to use is called random int. And the way I'm going to code this is, now before I talk about coding, one of the things I want to point out is random integer or random int samples integers from a defined set in a uniform fashion. So if I define random int on the calculator with a 0 and 1, what that means is the calculator is going to sample from the set that only has 0 and 1 in it, in the set, Okay, so random int on the calculator is going to sample from the set 0, 1 in such a way that 0 and 1 are equally likely. So the coding I'm going to use is that 0 equals tails and 1 equals heads. So now I'm going to go to the calculator and show you how to do the simulation on the calculator. So what we're going to do is go to Math, we're going to go to PRB, and we're going to choose number 5, random int. Now your calculator screen, if you're following along, probably looks a little bit different than this one. This is a newer version. But still, you will have PRB under Math, and then this part will look the same. So we'll choose number 5. And again, on your calculator, you probably, and actually, I think what I'm going to do is just take a minute, and I believe if I put my calculator back into classic mode, let's see what happens. I'll put my calculator into classic mode. So I think most students out there probably have an older version of the calculator. Let's see if this looks different now. So if I go to PRB, try this again, choose number 5. No, it doesn't. All right, so I guess that's not the case. So in any case, I'm going to type in the lower limit, which is 0, and then the upper limit, which is 1. I'm going to leave in alone for the time being, and then I'll choose paste. Now, if you have one of the older calculators, when you selected random int, what you saw was just random int come up on your home screen. And what you need to do is just type 0, 1 and then close the parenthesis. Now, to actually have the calculator take a sample, what I need to do is press enter. So that 0 means I just flipped a tail on this coin, on this fair coin the calculator is simulating. And each time I press enter, this represents a flip of the coin. So I just flipped another tail, and a head. Okay. So in fact, what we can do now is we can create a simulation on the calculator. Or what I've done is I created a simulation on the calculator where I'm actually flipping a fair coin. And again, I know it's a fair coin or a hypothetical fair coin because the calculator samples randomly from the set 0, 1 in such a way that 0 and 1 have the same chance of being selected. Now let's look at this problem from a different point of view. Okay, let me see. All right, so I want to reset this. So, okay, that'll work. All right, so now let's think about this in the context of a hypothesis test. So what we're going to do is we're going to address the question: is the Super Bowl coin fair? And I don't want to get too specific here. I know there are different coins for different Super Bowls, but let's just say for a particular Super Bowl, we're interested in the question: is the coin they're using to start the game, is that a fair coin? Let's set up the statistical hypothesis now. So we have a null. What we would do is give the coin the benefit of the doubt and say the coin is fair. In the alternate, we'd say the coin is not fair. And again, it's a dichotomy because the coin is either fair or it's not fair. Okay, so it makes sense statistically. Now, as we start to move into using mathematics more to make these decisions, one of the things that we need to do is we need to translate this problem from like a verbal type sentence in the null and alternate into some kind of a variable that we can use to model the situation. And so what we might say is we might define P as follows. So we might say P is the probability of flipping a head. Then our hypothesis could be written as follows. So we might say that the null is that P is equal to 1/2, meaning there's a 50% probability of heads. And the alternate would be that P is not equal to 1/2. So notice how the original hypothesis I wrote down is really the same as the one that the one in terms of P, the probability of flipping a head. Now, we're going to focus on heads. This problem would work the exact same way if we focused on tails. Now, what we really need to do if we're going to test this coin is we need to design an experiment. All right, and what we're going to do is flip the coin 10 times, say. We're going to flip the coin 10 times and we're going to count the number of heads. And now I'm going to define a variable, a different variable now. I'm going to define what we call a random variable, and this will come up later on in the next lecture as well, but this is sort of foreshadowing stuff to come. And I want to talk about this sort of in context of the simulation part as well. So I have a variable now, x is going to be the number of heads. So what I'm going to do is create a table. I'm thinking about this sort of like a function, really. But so I'm going to create what looks like a function table. And over on this side, I'm going to put what the domain of x. I'm going to run out of room. Doggone it. I don't have an eraser, do I? Let's see. I don't think I do. This is an older version of PowerPoint. All right. Let's see. Well, so I would have a 9 and I'd have a 10 down here. I'm just kind of running out of room. I should have left myself more room. The other thing that's going on, you might have noticed, I have a new computer I'm using to make this particular video, and it's frustrating me because it seems to be slower than my other computer, which is strange, and that's why it's like writing so poorly. Anyhow, I haven't solved that problem, but I'm going to go ahead and endure this and try to get this video made the best I can. I'm going to start over with that table. So let me go ahead and redo this here. And that's the other reason why I'm not talking when I'm trying to write, because here, check it out. When I try to write, it makes matters worse. I don't know if it does or not. I think I've noticed that when I'm trying to write and talk at the same time, the computer seems to lag, but maybe I'm wrong. I don't know. Let's see. If I write really slowly, it seems to do better as well. Yeah, see, notice I stopped talking and it wrote better. In any case, all right, so now I have my table. Looks a little bit better. I got all my x's. This is the domain, really, of the function that we're going to build up to. Notice if we're going to flip the coin 10 times, we could get 0 heads, 1 head, 2 heads, up to 10 heads. Over here, what I'm going to do is create a tally to keep track of the number of heads and tails. Now I'll go back to the calculator. Remember, we're going to simulate this. So I want to show you one other trick. If I come back here and use second enter, bring up the past command that I did, and I put a comma and then a 10, what the calculator will do is it'll generate 10 zeros and ones at the same time. In other words, it'll do the simulation of 10 flips in batches. So now I've got 10 zeros and ones. And so notice there are 4 heads here. The other thing I want to point out is I chose 0 and 1 purposefully because if I sum this set, the sum is going to be the number of heads, because 1 plus 1 is 2, plus 0 is 2, plus 1 is 3, plus 0 is 3, plus 1 is 4, plus the rest of the zeros is 4. So notice that let me show you. On the calculator, we can go to second stat, which takes us to our list menu. And sum is a list operation, so I go to math and I choose number 5 for sum. And everything we do on the calculator ends up getting stored in answer. So that set of zeros and ones has been automatically stored. And I hit clear for some reason on accident. Let me redo that here. So I'm going to go over to math, select sum, and then go second, take the opposite for answer, close that parenthesis, and press enter. So the first simulation of 10 flips of a fair coin ended up with 4 heads. So now let me show you another even more streamlined way to do this. All right, so if I bring back random int, and this is deep recall, so if I go second enter twice, I get back to the original random int feature that I was using on the calculator. And what I'm going to do is put the cursor all the way in front. Now I'm going to go second delete to int. Then now what that does is put the calculator in insert mode. Then I'm going to go second stat math and paste a sum in front. Then I'll go over to the other end and close the parenthesis here. And what the calculator can do is actually two steps at once. It can get the sequence of zeros and ones, the random sequence of zeros and ones, 10 of them, and then it can sum them all in the same step. So now when I press enter, I'm getting number of heads. So I got 4 heads in the first simulation, 5 in the second. Now I can just keep hitting enter. So I got 4, 5, 5, 6, 7, 5. 4, 5, 5, 6, 7, 5. So let me go back here and do my tally. So I got 4, got a 4, 5, 5, 6, 7, 5. What I can do is, now notice, this is what we're doing. What I'm doing is I'm creating an approximation of the distribution of the number of heads out of 10 flips on a fair coin. That's what this simulation's all about, and it's one of the things that makes simulation so useful. So I'll press enter a few more times. So I got a 3, 3, 7, 5, 7, 3, 3, 7, 5, 7. So I'll go back and record that. So let's see, that's a 3, 3, 7, 5, 7. And notice I can do this pretty quickly. I can do quite a few of these. Do a few more. 2, 6, 3, 4, 4. 2, 6, 3, 4, 4. So we got it. 2, 'I already forgot. What was that now? Let me go back and look. Let's see. Was it 2, 6, 3, 4, 4? 2, 6, 2, 6, 3, 4, 4. And what I would do is I would continue to simulate, and I would get a better and better idea. And what the tally is really keeping track of is the frequency of heads. Okay. Now, now once I get this frequency table done, okay, and again, I would recommend doing, 50 simulations. It doesn't take that much time. Okay, so put an X over 2. And so what you're beginning to see is, again, the distribution now viewed graphically. Now here's what we got to think about, okay, in terms of the hypothesis test. If the coin is fair, okay, if the null is true, we expect to get a 5. Okay, so if the null is true, we expect x to equal 5. Now, the alternate assumption for this hypothesis test was that p was not equal to 1/2, which means this direction would be extreme, or what we could say, that for the null, values in that direction would be rare. And values in that direction would be rare. And again, you want to think about, a couple of things to think about. Number one, I'm simulating the distribution for the null. So this graph that I just drew represents the distribution for the null hypothesis. If the alternate turns out to be true, or the distribution for the alternate would either have more, it would either have more, if say p was less than 0.5, then we would expect more x's down on this end. If p were greater than 0.5 or 1/2, we'd expect more x's on this side. Therefore, the direction of extreme here is two-sided. Okay, so the direction of extreme is two-sided. Now, let's talk about a decision rule for a moment. So it might make sense to define a decision rule as follows. And again, there's more than one way to do this. So a reasonable decision rule here might be to reject h naught if x is less than or equal to 2 or x is greater than or equal to 8. Now, suppose that I actually flipped the coin 10 times. And ended up with 9 heads. And that would be quite a result. So we flipped the coin 10 times, we end up with 9 heads. Now the correct type of error that we should, first of all, our decision would be to reject the null hypothesis because x equal 9 is greater than 8. So we would be in the rejection zone over here. So our decision is reject the null hypothesis. Now the correct type, the type of error that we need to assess is type 1 error. What our simulated distribution is going to allow us to do is estimate alpha. Now, I'm not going to go back and spend a bunch of time doing the simulation for the lecture because, again, I think that the idea came across. I could just go back to the calculator, hit enter a bunch more times, keep track of the number of heads, and continue to build my graph and get a better and better approximation for what the distribution looks like. But here's how, just based on these few number of flips, I would estimate alpha. So the decision rule splits up the x values like so. All right. So the x values that are in the rejection region over here and over here are the ones that are going to trigger a type 1 error. Now, I haven't gotten too far along in the simulation, but I can still estimate alpha. It's going to be a crude estimate, but I had one result within the rejection region from my simulation. So we're going to have one. Our estimate for alpha is going to be 1 divided by the total number of simulations. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So my estimate for alpha here is going to be 1/16. Now, in a similar way, I can actually estimate the p-value. And to estimate the p-value, what I want to do is look at the actual data value and think about what the chances of getting a value for x that's at least as rare and unusual as 9 if the null is true. So for the p-value, I'm going to look at the frequency for 9 and 10, but since it's two-sided, I've also got to come down here to the left side and consider these values. So in this example, my p-value, my estimate for my p-value is going to be 0. Now, if you did the simulation more times, you would end up eventually getting some 0s, 1s, and 9s, and 10s. And so if I did this simulation instead of only 16 times, say 100 times, then my estimate for the p-value would be non-zero. And one of the things that's in Chapter 7 also is this concept of the law of large numbers, which says that if you repeat a simulation many, many, many times, 1,000,000 times or 100,000,000 times or something, many times, that those approximate, or what we call relative frequencies, the relative frequencies for each value of x are going to approach the true theoretical values. And we'll talk about this more as we go through the lecture and go through Chapter 7 or in future lectures. All right, so next I want to talk about how we do simulations on the TI. So here's a definition. A simulation is the imitation of a random or chance behavior using random devices such as random number generators or a table of random numbers. The basic steps for finding a probability by simulation are as follows. Step 1, specify a model for the individual outcomes of the underlying random phenomenon. So in the case of a fair coin, the model was random int. And then step 2, we're going to outline how to simulate an individual outcome and how to represent a single repetition of the random process. So I guess in step 1 we could say the model is, sample from a uniform distribution, or the concept is, we need to sample in such a way that the probabilities are equally likely. In step 2, what we did is, or what I did in the previous example was I used random int, coded 0, 1, 0 is tails, and 1 is heads. And then the third step is to simulate many repetitions, say n times, and then determine the number of times x, the number of times x that the event occurred in the n repetitions, and estimate the probability of the event by its relative frequency. So here's another example. Let's talk about another example of fair die. So in this case, we want to design a test to determine whether or not a particular die is fair. And the way we're going to roll the die or test the die is by rolling it twice. Okay. So this example is going to come up in the next lecture as well. So I'm just going to give kind of a thumbnail sketch about how to do this one. Now, when we think about rolling a die and simulating rolling a die, okay, my picture of a die. We know that when I roll a six-sided fair die that there are 6 possibilities, okay? And so this is, again, an idea that's going to come up in a future section, but I'm going to define something called the sample space here. These are all possibilities that could happen from the random process. So the sample space for this particular example is going to consist of the numbers 1 through 6. Okay. So I'm going to use random int again, but this time I'm going to code it with 1 through 6, 1, 6, and that's going to again give me the boundaries. Notice this gives me the boundaries of my sample space. Okay, so random int will sample uniformly from the set 1, 2, 3, 4, 5, 6. Let's go back to the calculator. Now, in the design, what I said was we're going to roll the die twice and sum the pips. And what I want to show you is a really slick way to do this, okay? So I'm going to do 100 rolls of the die. And again, you got to remember, we're going to roll it twice. The actual physical die we're going to test, we're only going to roll it twice and sum the pips. But I need to do this simulation over and over again so I get an idea of what the distribution looks like. So I'm going to math, PRB, choosing number 5, random int. The lower limit in this case is 1. The upper limit is 6. This time I'm going to put n equal 100 because I'm going to actually have the calculator roll the die 100 times. I'll paste that in. So again, if you have an older version of the calculator, you will not have seen that window to fill in. What you'll see is just random int pop up, and you'll have to type in manually 1, 6, 100 and close the parenthesis. Now what I'm going to do, here's the trick. What I'm going to do is store those 1s, 2s, 3s, 4s, 5s, and 6s in L1. So I press store second 1 for L1 and then press enter. Okay, what the calculator just did is rolled the die 100 times and stored the resulting number of pips for each roll in L1. I'm going to do a second roll set of 100. So I'm going to press second enter to bring back the previous command. And this time I'm going to store the sums in the outcomes in L2. So now what I have is 2 lists that each have 100 rolls of a fair die. And again, I'm looking at the sum. So one of the tricks we can use here is I can go second L1 plus second L2. And what the calculator is going to do is add. So it's going to take 1 plus 2 is 3, and 5 plus 2 is 7, and so on. And we'll store the sums in L3. So notice what I've just done is created a set of 100 random or 100 sums based on random rolls of a fair die. And that's now in L3. And again, I could have done 500 pretty easily, but I'm going to do 100 this time. Now, we've already talked about histograms, but I want to show you how we could create a histogram here to display our results, okay? Now, I already have the data in a list because the data that I'm going to use, it comes from the simulation, and that's in L3 already. So I'm going to go second y equals for stat plot, choose plot 1, turn it on, select on, and the histogram is what I want to draw, so that's already selected. Now my X list here is L3 because that's where the sums got stored. So now the stat plot window is configured. And I'm going to go to my window settings. I have to be creative now about how I put in these window settings. So I want to start it. Now, when you think about it, you know, the smallest sum possible is a 2, because that would be rolling a 1 and a 1. 1 plus 1 is 2, right? There are no zeros on the die, just 1 through 6. Let's start my histogram off then at 2. Now, the largest sum is going to be 12, and that would be rolling a 6 and a 6. So I need to go to 13 here because of the way the calculator draws histograms. It's going to need, it draws histograms by taking all the values of the variable x, in this case, that land on the left boundary, and it throws it in the right-hand column, or what we call class, the right-hand bar. So I need to go one more past 12. And I want x scale to be 1 because I want the class width for my histogram to be 1. What that means is every sum will be represented by an individual bar. And y min of 0 makes sense. I'll just leave it at 0. That would be a frequency of 0. And I'm going to guess for the y max. I'm just going to guess 30. I really don't know what the right y max value is in this case. And then I'll set y scale at 5, which means when we look at the y-axis, we'll be counting by 5s. All right, so press graph. And here's what the histogram looks like. And so again, what this is showing is a distribution for the sum of 100 iterations of rolling a fair die twice and adding the pips. So again, if we were going to do a hypothesis test, and again, I'm going to do the hypothesis test. It'll come up in the next lecture. I just wanted to demonstrate in this example how we could simulate rolling a fair die and then summing the pips. All right, well, that's it for this lecture. I'll see you next time.